Hello and welcome to another session of the Digital WE Days. My name is Stirn and I will moderate this webinar today. The topic of today is the single wire IC LED under EMC perspective. Our speaker today is Adrian Stirn. Adrian, hi, welcome. Cool to have you here. He works as a technical lead at the EMC laboratory. IC LEDs offer sleek lighting effects with simple control, but the single wire operation can introduce EMC challenges. How do you design them without compromising performance? Let's explore the key considerations. Stage is yours, Adrian.
Yeah, thank you very much. So welcome also from my side, guys. Today is last session and we will talk again about EMC. During my time in the EMC lab, I have seen a lot of problems, especially when we have asymmetric buses leaving a PCB. And also we had a big project with a lot of IC LEDs in the past, and where we've seen, okay, we should do something, and we want to explain you how you can integrate these IC LEDs in your application without having any problems. So we will start with a setup that a student of us created in the end of last year, which can be an example for you and give you an idea how to design an MCU together with an IC LED. We will do two experiments today. We will have a focus first of MCU and IC LED strings on a single board. And then in the second step, we will split this up because often you like maybe not to have the MCU more or less in your LED panel, but you want to have to separate it somewhere. And we will have a look on where can be the challenges here. So for those of you who don't know me so far, I'm Adrian. I'm responsible for the EMC labs at Electronic Germany in Waldenburg, the headquarters, and also for Munich. I'm doing EMC since 2016. Also, I did some EMC stuff during my electrical engineering studies. And so I'm doing a lot of customer support, especially pre-compliance EMC measurements and EMC debugging. So we try to optimize our customers' devices for passing the EMC tests. Here a small insight in my EMC lab. So some advertisement for us here. So if you have some trouble, please feel free to contact us. Here you have the email address. Feel free to contact us. We like to support you, of course. Here you can see my fully anechoic chamber where we do the radiated emission and immunity testing. And we have also some shielded rooms here where we can do the conducted emission and immunity testing and also transient testing. Here a small insight into our lab in Munich where we have a 3-meter fully anechoic chamber and a shielded room for the conducted and transient testing. So now let's get started with the application. So first of all, let's have a short look on what is an IC LED for those of you who don't work with it so far. So an IC LED is an LED with a VCC pin and a ground pin, and we have an RGB lighting chip, and this one is controlled by the IC, and the IC is getting an protocol here with 800 kilohertz and 24 bits controlling the RGB LED chip, so you can more or less steer the color and the light intensity here. Furthermore, we have a digital output, and so the protocol can be sent from one LED to the next. So the first LED in the string will pick up the first 24 bits of the string and will push the rest of the string to the next LED. So we can more or less daisy chain a lot of IC LEDs by only one single bus. In our experiment, we will use an expressive ESP32 microcontroller working with 3.3 volts, but the LEDs are working with 5 volts, as you can see. So we will do a board with up to 5.5 volts input, and we will more or less supply this ESP32 with a LDO, and then we need a level shifter from the 3.3 volts to the 5.5 volts of the LEDs. For EMC testing, we will have then the following ports and the test plan. We will have a 5.5 volt DC input. On this DC input, we can do conducted immunity testing with a CDN M2. We can do a burst testing where we will use the capacitive coupling clamp. and we will do the conducted emission testing according to CISPO 16 with a 550 microhenry listen. So again, as I mentioned in the first webinar from today, I like to more or less measure the DC input as an AC input. And my idea behind this, when I pass the DC with the DC input, the AC limit, I will also pass it with an AC to DC converter, which is more or less maybe not reducing our noise that we are producing with our board here. A surge test we will not perform because I guess for such a board or a lightning equipment you will have a short connection between your AC DC power supply and your board later on. Then we will do the radiated emission and immunity testing, of course. And then the question is, you have different possibilities how you can power up these LEDs. So we will work with half power through all of these results that I show you now. But more or less in our experiment we have seen we don't see a big difference between full power and half power. So that is not a big influence here for the EMC performance. In the first step now we will have a look on everything is on one board. So we will have the microcontroller and the LED string on a let's say one compact board, short traces. And we will start with a board that has a common ground plane. That is, as we would expect from EMC perspective, the best way to do the design. But of course, sometimes you will have splits in ground planes or even no ground planes in a system. And then the question is what can happen here? So this is what we will have a look on then. We will do a board without a ground plane where we only have 100 nanofarad MLCC for decoupling. That is, by the way, mentioned in the data sheet and also used here with the ground plane. And then on top of that, I will add some ferrites in the data string to reduce the frequency range of the signal somehow. And what we try to do is then to control the high frequency noise above 30 megahertz, and you will see it later on. So first of all, the decoupling cap. How does a decoupling cap works? So we want to have the decoupling cap giving the energy for the IC and also the data string. So there are high frequency currents will be start here and will go inside the IC LED and it will travel to the next LED and returning via the ground pins here. So now the first shot of the PCB had some, let's say, error in the traces because you can see here in blue a very long ground trace. And on this very long ground trace also this decoupling cap is more or less connected with this via. But on the other hand, we have a very long ground strip for the output of the IC LED. And when we have a look on the last, let's say, two LEDs of the string here, you will see that we have a very, very long trace or loop for the high frequency currents to run. When we start here with the digital out, going to the digital in, returning via the ground here, and then the current needs to run back all the way to this ground of the cap. That of course doesn't make sense because we want to have this loop as close as possible since we call it also decoupling, right? So what was done here is opening up the trace and connecting the ground pad of the capacitor to the upper ground trace. And so that is also something that we are typically doing every day in the EMC lab when we see, okay, we need to somehow control the decoupling loops, reduce them. So that is a typical hands-on work here. And in the end, you will see we reduce this loop from the complete loop area, of course, to the, let's say, smallest possible one here when we don't use a ground plane. So when we want to reduce the frequency in this loop here, which you can see, then we can add some frequency-dependent losses where we can use, for example, a chip-beat ferrite. In this case, we were using this article number, and you will see it later on in the results. That can have also an influence in the high frequencies, of course. And here is my favorite design. We are using a common ground plane completely without any split. And then we can see the wire from the IC LEDs output ground and the decoupling ground. And so we can more or less go the shortest way for the high frequency currents, going from this LED to this one, going into the ground, and then the current can return in the ground plane below the trace, giving us the smallest loop as possible. One quick view how we can do a split system. We can use the saw and remove the MCU part of the PCB here. Note we are using for both PCBs a ground plane here. So we have a MCU a PCB with ground plane and the LED panel with a ground plane. You will see later on we will get enough emissions when we just use 1 meter cable in between. The cable here is a self-made twisted pair, so maybe something that you will also have realistic later on in your application. Therefore we are connecting VCC, ground and digital out of the level shifter to the first digital in here. So, quick overview on our PCB which we are using. We have the 5.5 volt input. We have our LDO section connecting this one here to the MCU. And here's our level shifter from 3.3 up to 5 again. We have the possibility to do some programming here on the MCU. And we have some switches, so we can also change between the different programs that we have on board. So during immunity testing we had the first issue with the LDO. You can see here that the 3.3 volt output of the LDO is disturbed. You can see that it goes down to something like 2.5 volts and then going up again, and this causes a restart of the microprocessor. So with this you cannot work during immunity testing because this is the weakest part then. So we cannot analyze what happens with our LED string when we even get problems with the steering MCU. So we added some ferrite here as a PI filter with 2 MLCCs and also an output MLCC, and that gives us more or less the performance that we can go up to the maximum test level that we wanted to achieve. Okay, so then let's have a look on the EMC test results. We are starting with everything on one board first. You can see the test setup here. This is this board with the MCU and the LED string. And it's connected with a 5.5 volt input cable, and the input cable is running with more or less 1 meter horizontal in our quiet zone of the fully anechoic chamber. When we split up the boards, we will still have the 1 meter cable in this cable harness inside the table, but on top we will also have the 1 meter cable running from the MCU to our IC LED panel. We use this setup for radiated emission and immunity, of course. So in the next slide we will have a quick look on the EMC test results. While the slide is loading, here you can see the results. In green we have the emission results for the IC LEDs MCU on a single ground plane without any split. And you can see we have a lot of margin up to the limit. While when we have a look on the blue result, this is the curve where we use only the decoupling cap and the ferrite. So this still gives us a pass, but in vertical you can see we get near the limit. So, but it helps us to pass the test because when we compare it with the yellow curve, you can see when we only use let's say the IC LEDs with the decoupling caps and we don't have a ground plane, we will be above the limit even in a very compact device. So that is the first conclusion for me. The best option how to implement it from radiated emission point of view is to use a ground plane. But this is something normally we as EMC guys would expect. Now you can see the setup for the conducted emission measurement here. We are using the CISPO 16 listen. The issue with this is it has already a high series inductance inside, and this will influence our IC LEDs. So the controllers for this low voltage stuff don't, or let's say safety voltage stuff, don't like to have this big series inductance. And for this I'm adding a 1 millifarad elco to more or less stabilize the system. Then let's have a look on the conducted emission measurements. In green again we have the board with the ground plane, and in purple and red we have the boards without a ground plane. More or less what we can see is that the ferrite in this low frequency range is not helping to reduce the noise, and we can also see that it's near or on the limit here, maybe also slightly above the limit. In general that is at first not a big deal, because normally you will never have a 5.5 volt DC grid, of course, where you will connect it, I guess. But the issue is at a certain point, maybe your AC to DC power supply will not filter this common mode noise here. And you can also couple the noise from your PCB through your power supply into the grid. Again, we can see from performance point of view, from the conducted emission, the ground plane PCB is working best. Now let's jump to the immunity testing. What happens when we get immunity issues with IC LEDs? Here are different screenshots from the testing. So at certain points we had a loss of string, so some IC LEDs were not lighting anymore. But we had also some let's say changes in slide color changes and holes in the string, but we can also have a disco light. So everything is possible. During the radiated immunity testing, with everything is on one board, all the devices pass 20 volts per meter. Only the non-filtered device get problems at higher field strengths than 20 volts per meter. Here you can see the setup for the conducted immunity testing. We are using the CDN M2 and injecting common mode the high frequency noise on plus and minus to the board, and we are 10 centimeters above the referential ground plane. So the noise is traveling from the CDN inside our device under test and returning via the stray capacitance back. With this setup we passed 20 volts for all the boards. Now a quick insight in the burst testing. You can see we are using the capacitive coupling clamp for testing, but on the other side the issue is that we will have of course the bursts running to our device under test, but of course we will also test our power supply. Especially laboratory power supply don't like that very high burst levels when we talk about 4 or 5 kilovolts testing. To be sure that we don't influence the voltage control of our lab power supplies, I'm using one of our Magic DC-DC converters and a 12-volt battery. So the converter is stepping down 12 volt to 5 volt, and this is, for example, a part where we know that we can go up to 5 kilovolts with capacitive coupling testing. So in the end we will know when we get a problem here, it's not due to the power supply that fails. For the ESD testing, we only can test the horizontal coupling plane, because of, later on when you have a direct discharge inside your circuit, you will get a problem that you can damage the semiconductor. So the ESD level that you can read in the data sheet often is only made for the production, means the human body model. But when it comes to ESD testing, according to the EMC on system level, the current is 5 times higher than, for example, in the human body model. And therefore, the semiconductor components are not made for direct discharge. Means in the end, the LED panel will be somehow put into an enclosure, so a direct discharge into the traces is not possible. Now we are simulating an indirect discharge by only here shooting on the horizontal coupling plane. Again, I'm using our Magic module board as a power supply to be sure that we don't get an overvoltage due to a not well-regulated power supply. And then I want to show you some video here. This is the notebook that I'm using in front of the shielded room where we do transient testing. It is more or less used for doing burst and surge tests. And here you can see a USB hub, and this USB hub is disturbed by the ESD gun inside the chamber. You can hear now how the USB hub is connecting and reconnecting, and here the colleague is using the ESD generator with 30 kilovolts. You can see the LEDs are not flashing, the light is stable, but on the other side you can hear how the USB hub is disconnecting. So we can see when we do it right, we can get a really good performance, and we can even see that other devices outside the shielded room are disturbed. So let's come to a first summary of the immunity results. So we start with the board with the ground plane. you can see that we will pass with the maximum available level, test level in my laboratory, which you can see here, means at least 20 volts per meter, but going up to 40 volts and 30 volts. And above 1 gigahertz, we can go up to 10 volts per meter. For the conducted immunity testing, we can pass the 20 volts without any performance loss. And with burst testing, as you have seen, we can go for 5 kilovolts with the capacitive coupling clamp, and like in the video, 30 kilovolts for ESD testing. When we now go to the board without a ground plane and without ferrite, we only pass 20 volts per meter for the radiated immunity. Afterwards, we get an influence when we have higher levels. When we go for the burst testing, we can pass criteria A without any loss of performance up to 1 kilovolts, and ESD for the horizontal coupling plane up to 6 kilovolts without performance loss. When we now add a ferrite into the data lines, performance gets better, not only for the emissions but also for the immunity. When you have, we are here, we are again able to pass the maximum level. But also for burst, we can go up instead from 1 kilovolt to 2 kilovolts, and for ESD we can go up to 10 kilovolts. Now let's split up the boards and see what happens. So as you have seen, when we remove the ground plane, things get worse. We get more emissions and we get immunity issues, and that is the same what we now expect for the split from MCU and the boards. In red, you can see the curve with the MCU and the LED panel splitted with only 1 meter cable. You can see that you are far above the limit from beginning more or less 30 megahertz up to at least 200-300 megahertz. As a comparison, in green, you can see the EMC test results where everything is on one board with a ground plane, and in yellow you can see everything on one board without any additional measures. So we can see when we split MCU and LED panel, things become much worse, and we really need to think of what to do then. What happens on the conducted side of emissions? In green, again, the board with the ground plane, that is 10-20 dBs below the limit, and in red, the board where we don't have a ground plane. And now, again, we get on top more emissions when we split up the board. That is what you can see in purple. And here, especially when we have a look on the average, we are more or less 10 or even more dBs above the limit. And now the question becomes interesting: is our AC to DC power supply capable of attenuating this noise in that frequency range? I guess here we could get a problem later on in the field. So now some ideas what we can do to optimize the EMC performance when we want to split up the MCU and the LED panel. So first of all, we could implement a shielding. In this case, of course, we are in the EMC lab. We are using aluminum tape and aluminum foil and copper tape. So what I'm doing is I'm connecting still VCC and the data string between both, and then I'm using both ground planes from the MCU and from the LED side, connecting this to copper tape and then the copper tape to aluminum foil. So what we are doing is now we use the shielded cable to extend our ground plane. In the end, more or less, we are simulating a complete ground plane between both boards. On the other side, on the other hand, we are doing some filtering. So we use an unshielded cable, but we use a pi filter on the data out from the level shifter. We are using 2 times 220 picofarads and a series ferrite. The problem was when we are measuring with an oscilloscope probe on the data in pin of the first string LEDs, we have seen that we are above the 5.5 volts due to the long inductance from this 1 meter cable and high frequency signals. So what we did is we added an additional 220 picofarad MLCC to reduce the maximum voltage level below the 5.5 volts to avoid a damage of these ICs inside the LED. And additionally, we can of course add a common mode choke on the input. We have now a long cable with high frequency. We can have differential mode to common mode conversion. And if we want to limit the complete antenna system, we can add a common mode choke here. And when we're using here a common mode choke, especially a sectional with sectional winding, we also add some MLCC for using the stray inductance for differential mode filtering. Now let's have a look on the results first. Conducted emissions. We're comparing now the shielded cable and the unshielded cable. And you can see again, unshielded cable 10 or 15 dB above the limit. When we use the shield, the results are now comparable more or less to what we have seen, the board with the ground plane, and we are 20 dB below the limit. So for emission, this seems to be a quite possible way to work. For radiated emission, also the shielded cable looks quite good. In red, you can see far above the limit over the complete frequency range. With the shielded cable, it's comparable, like having everything on one PCB. Then we will implement the filters in the full stage, where we will have the ferrite and the common mode chokes, and we will have also in blue, where we have the reduced filter, where we only use the pi filter on the digital output of the level shifter. And you can see especially from 20 to 30 megahertz here, the common mode choke is starting to reduce the common mode noise, and we're going down with the emissions. Nevertheless, the results in the conducted range are not that perfect when we are using filter components instead of the shield. Of course, the frequency range of these components is higher than the 10 megahertz. Means we don't have that big influence in the lower frequency range. On the other side, our AC to DC power supply will filter in this lower frequency range the differential mode noise, but also the common mode noise in a better way. Let's have a look on the radiated emission results. In red, again, split of the system without any measures, and in blue and in green, the filtered versions. In blue, you can see in the lower frequency range, the emissions are slightly higher, and that is where the common mode choke is also perfectly working and reducing this noise. From emission point of view, we can show more or less when we think of the AC to DC power supply, with the split system, we can pass the test when you use a shielded cable or when we use the filter components. Now, when we talk about immunity, things become a lot more interesting. We start with the splitted system without any measures. You can see that we can pass 3 volts per meter without any performance problems. But when we go to 10 volts per meter, things become tricky and the IC LEDs get disturbed. We can not pass the conducted immunity testing with 3 volts. So more or less a commercial pass with this system is not possible anymore. As you can also see, during burst testing, the system gets disturbed, and for ESD, only 1 kilovolt on the horizontal coupling plane is possible. When we now add a shielded cable, things get a lot better, especially for continuous disturbances. You can see we can go again up to the maximum levels like before. So there's the full performance, and also for the burst, a 2 kilovolt with criteria A is possible. So that is an absolutely nice performance where we can be very happy here. Also, the 15 kilovolts are nice for the ESD. Now with the filter, things become a little bit tricky. We have a good ESD performance. We have also acceptable performance for continuous disturbances. Maybe the 10 volts, that is something you need to figure out for your application, if this is acceptable or not, depending on if this is just for, let's say, some lighting, or if it's something for signaling in industrial applications. Then this can be not enough as a performance, especially when it's safety relevant, giving an operator some ideas if something is good or not in a device. Then I would prefer the shielded version. Otherwise, I guess it's okay. But we can see we have still issues with the burst. And that is something that you can solve, for example, with software by always rewriting the data string. So finally, all the results I presented can be read in the application note 013. We have also some more information about the design and how to go on, also some measurement with the scope, so a very interesting application note, I guess. And from design recommendation point of view, the best option is always to have MCU and IC LEDs on a single PCB with a ground plane. I guess the results show clear that the performance is best when you do so. And you can also see that it is very dangerous to split up MCU and IC LEDs, especially when you don't have a ground plane. We can recommend, if it's required, to split up, because maybe you don't like to have your controller near your lighting panel, that at least you can use a shielded cable. And if this is too cost sensitive, you can think of using frequency dependent filter to deal with the frequencies that can occur. And for me, from EMC point of view, the last point is even the most important. Please guys, when you do designs, think of if it makes sense to go with I2C buses, SPI, UART, MII, or whatever buses that are asymmetric from PCB to PCB. A lot of problems in my lab and with customer designs is always asymmetric buses leaving a PCB. Please don't do that. Thank you. So thank you very much for your attention. I guess it's time now for the questions, Silas.
Yes, thank you, Adrian, for your interesting presentation. Now we'll come to your questions. Before we start with the live Q&A, I will share the handout, and now everybody can download it. Okay, yeah, I see a lot of questions in the chat, so we can directly start with the first question. Do you have similar tests for one wire?
One wire? What is one wire? Yeah, I guess these are one wire IC LEDs. Yeah, but maybe it's meant 2 wires. I don't know. But for 2 wires, I guess the results will be the same.
Mm-hmm. Okay. Okay, thanks. Then next question. It's a question about the app node. In 00009, the tube output current for IC is 3 milliampere.
13 milliamps.
3 milliamperes. Yeah. Does it mean that for specified luminous side for each LED, the value of current per LED is about 4?
I think that is something we will hand over to our PM guys. They are more into the specs of the IC LED. I think we will write you an email regarding this question.
Perfect. Then next question. Maximum switching frequency at DIN that ensures the LED is fully on and fully off.
Oh, DIN. Is this I'm not sure if this is a question regarding the protocol. I guess it's best is to read this in the app note. We have it described detailed here how this works. So in general, the IC LED, I'm not sure if that was the question, is working. You're sending a 24-bit data string, and with this data string, you're programming the internal controller, and the internal controller is then giving you the wanted light.
Mm-hmm. Okay, then this one. I missed the part. The emission test, is that with or without active programming? You're right. Absolute good question. Yeah, it's with programming. We have a continuous sending, so something like every half second, and we are measuring at least with 1 second. So we are sure that we measure everything. Mm-hmm. Exactly. Yeah. Yeah. Okay. Perfect. Then.
Yeah, good point. Because you see, when you send the data, the emission goes up. Yeah.
Mm-hmm. What is the delay? DIN and DIN out?
I don't know.
Okay.
Yeah, I think that is something for the PM guys.
Mm-hmm. Is it also related to the length of the wire?
The emission and the immunity performance is of course also due to the wire length. Normally, especially the quarter length wavelength and half wavelength are radiating very good. But when we talk about 1 meter, that is something that we are using typically in EMC world and EMC testing world. You get normally emissions starting at 30 megahertz. Of course, the longer the cable is, the lower the frequency gets where you radiate. Yeah, especially interesting when you have an application with a limited size and you want to somehow control the frequency that you send on the DI or the D out from the level shifter in this case. And I want to say, okay, I have only 20 centimeters. I calculate my critical wavelength, and then I can calculate also the filter.
Okay. Then next question. How we can interpret the result when vertical is worse than horizontal? Is there indicate for debug?
In this case, not. In general, yes. I think when we have open PCBs that we connect with some cables, more or less the cables are the antennas, especially in the lower frequencies. For higher frequencies, or when we have an enclosure, this can be very interesting, because when we have a horizontal slot antenna, we will get a vertical polarized electrical field. So especially when it comes to enclosures, this is very interesting, yes. Normally, let's say in the fully anechoic chamber setups that we do in our small chamber, we have more horizontal emissions because we have a lot of horizontal cables acting as the antenna.
Okay, thank you. Then next, and I think this was also a question for the PM, but yeah. Okay. Then this one. How can the SWE solve the issues during transient testing?
Yeah, how can we solve issues with software during transient testing? This is something we do quite often. In the last years, people get the feeling that it's something illegal, but of course it's not. In this case, for example, for transients, we have the criteria B in the standards, allowing that during the transient phenomena, we can have a change in the performance of the device. For example, the LED can change the brightness or the color for the short time where the transient occurs. Afterwards, the device should be back in the operation mode. So what happens when during testing the color is changing? I can just resend, let's say every half second or second, the command to get the or to keep the same color as we had before or in the start of the test. And of course, that is not a software you only use during EMC testing. You will also use it later on, because transients occur quite often. When you switch off the light, you can see the spark inside the switch, inside the mechanically switch. That is the burst that will disturb later on your devices. So this is something that happens. And also the only phenomena that someone who is not into electrical engineering understands is the ESD. You touch something and then the color's changing. That is something our customers really don't like.
Okay, thank you. Then I would say we have no more other questions. No. Okay. So if you have any questions, please write into the chat, and then the product manager or Adrian will answer them via email in the next days. So yeah, thank you, Adrian, for your time, for your presentation, and for the answers. Thank you for your attention. Now I will share the link to our homepage for the Digital WE Days. So we had a lot of other sessions during this week, tomorrow and on Wednesday. So we just now, this was the last session from today. Thank you. Have a nice evening, have a nice day, and bye-bye. See you soon.
Bye-bye.